Okay, hello, I am Miikka. I am a physics teacher and also, of course, a frisbee golfer. God damn it. Like a relatively advanced, intermediate slash advanced disc golfer. Played a little bit of in amateur competitions, played for 8 years now. So thinking physically, like physics and really like, you know, not vaguely, will help you to understand how frisbee flies. I think I'm gonna make a few videos about the numbers we can find on the disc. We can find the speed, the glide, the turn, and the fade, and of course the weight of the disc, or mass, as we say in physics, because this disk weighs different if you're in Jupiter or if you're in Earth. So, by the way, I usually teach in Finnish and I use the concepts that are used in Finland. So this might differ whichever country you are in. So if I'm using some kind of symbol or using a weird word, excuse me. I'll try to look for them online to use the correct English versions. Furthermore, in this video, I try to attach these numbers on the disk to physical concepts and try to also increase your knowledge about physics. So if you're like, for example, a high school student, this will really be good for you. So I recommend staying tuned if you want to learn physics in a fun way, I guess. Okay, so we're going to be making a concept map of the various concepts we are using. What am I zooming here? What the... I got this pen tablet basically used and still a little bit not sure how to use it. We're not gonna talk about massa here, we're going to talk about the mass, you idiot. Okay, so in physics we use kilograms instead of grams, so I'm just putting that in. This is of course in grams, 158 gram, this disc. I bought this for the missus. It's a wave. It's a really good beginner driver, especially in the not so heavy weights. So usually a lighter disc is easier. So that's our center concept here. I thought that I will introduce 3 concepts in physics today. So we will be starting with momentum, liikemäärä. So momentum, apparently I have to know Latin also. I don't know if you want to know the unit that is used for it, but let's put it in anyway. So kilograms times meters per second. Oh god, this map will look horrible. The symbol for momentum is P, at least in Finland, and the formula for it is just mass times velocity. So a heavier disk has more momentum, and a faster disk has more momentum. Not a huge surprise there, I believe. Okay, so what is momentum usually associated in physics? It's usually collisions. So for example, a car hits a truck and you can calculate speeds before and after the collision based on the weights, and of course you have to know a lot of velocities and so on to able to calculate things, but we can make a simple example of a kind of collision. So imagine this: you are playing in the rain, in the cold, in winter, and you throw the disc and a droplet falls on your disc and freezes immediately. That's a likely scenario here. So here is our disc before and here is our disc afterwards. Some droplets before they fall on the disk and make an ice puddle, whatever that is. Okay, so we need to define some symbols here first. So M1 is mass of the disk. Oh boy. Teaching in English is hard. Of droplets. Do you have 1 or 2 T? I don't know. Let's keep it that way. V1 is disk velocity in the beginning, and V2 is in the end. Well, that doesn't make much sense. Of course, the disk is stopped moving in the end, but you know what I mean here. How does the math look then? So in the beginning we only have the disk momentum, m1 times v1. By the way, this is usually the unknown, or I would consider this the unknown. There are plenty of stuff that affect the speed of the disk, so this is very you can imagine it's a disk going in a vacuum, and then for some reason there is droplets in the vacuum. But anyway, this is physics. So in the beginning there's only momentum of the disk. The droplets don't have momentum in sideways motion. They are only dropping downwards, so they don't have sideways momentum. Okay? So in the end there will be m1 plus m2 times velocity 2. Of course you need the brackets there to make it work. Okay, so what could we do with it? We could, for example, solve V2. So speed after the droplets hit the disk and freeze on top of the disk would be slightly reduced. So of course, if you think mathematically, if we only had m1 here, it would supista, the word. It would eliminate this m1 on top of here, so they would go away. The more we increase m2, more droplets coming in, the smaller this number becomes, and v2 gets smaller. Of course, that's common sense. More droplets coming on the disk, slower the disk goes.
So here's the example with 1,000 droplets. In the first line we have the mass of 1,000 droplets, which is around 30 grams or 0.03 kilograms. Then we have the mass of the disk on the second line. Then we have a release speed on the third line. I put in 30 meters per second, and that's 108 kilometers per hour, which is pretty high release speed, but doable, I guess. Then of course for the Americans I put it in miles per hour also. Then the calculation just pretty straightforward, and as you can see the numbers drop significantly with 1,000 droplets. But then you can also think, how often will there be 1,000 droplets hitting the disk?
Okay, so what are some different circumstances where this might affect the speed of the disk? Of course, having the droplets coming down and staying on the disk, even if they don't freeze, it might slow the disk slightly. Like if you think about droplet, how much does it weigh? Tens of micrograms or something like that. You need a lot of droplets. But other stuff, you could hit a bush, the branches of the bush will get some momentum off the disk and the disk will slow down. Or when the disk is sliding on the ground, it can hit some leaves or rocks or whatever. In that case, it's better to have a heavier disk because it will slow down less in that collision. This disk only weighs 158 grams. This is a really lightweight disk. Most of the disks are between 167 and 175. So only like maybe 2-3% of difference. It's kind of minor, but still it is there. It is there. It's definitely a thing.